scaling of our data centers. And every single time we scaled, we found a new phase change. When we scaled from DGX into large AI supercomputers, we enabled transformers to be able to train on enormously large data sets. Well, what happened was, in the beginning, the data was human supervised. It required human labeling to train AIs. Unfortunately, there is only so much you can human label. Transformers made it possible for unsupervised learning to happen. Now, transformers just look at an enormous amount of data, or look at an enormous amount of video, or look at an enormous amount of images, and it can learn from studying an enormous amount of data, find the patterns and relationships itself. Well, the next generation of AI needs to be physically based. Most of the AIs today don't understand the laws of physics. It's not grounded in the physical world. In order for us to generate images and videos and 3D graphics and many physics phenomenons, we need AIs that are physically based and understand the laws of physics. Well, the way that you could do that is, of course, learning from video is one source. Another way is synthetic data, simulation data. And another way is using computers to learn with each other. This is really no different than using AlphaGo, having AlphaGo play itself, self-play, and between the two capabilities, same capabilities, playing each other for a very long period of time, they emerge even smarter. And so you're going to start to see this type of AI emerging. Well, if the AI data is synthetically generated and using reinforcement learning, it stands to reason that the rate of data generation will continue to advance. And every single time data generation grows, the amount of computation that we have to offer needs to grow with it. We are about to enter a phase where AIs can learn the laws of physics and understand and be grounded in physical world data. And so we expect that models will continue to grow. And we need larger GPUs. Well, Blackwell was designed for this generation. This is Blackwell, and has several very important technologies. One, of course, is just the size of the chip. We took two of the largest, a chip that is as large as you can make it at TSMC, and we connected two of them together with a 10 terabytes per second link between. The world's most advanced SerDes connecting these two together. We then put two of them on a computer node, connected with a Grace CPU. The Grace CPU could be used for several things. In the training situation, it could be used for fast checkpoint and restart. In the case of inference and generation, it could be used for storing context memory, so that the AI has memory and understands the context of the conversation you would like to have. It's our second generation transformer engine. Transformer engine allows us to adapt dynamically to a lower precision based on the precision and the range necessary for that layer of computation. This is our second generation GPU that has secure AI, so that you could ask your service providers to protect your AI from being either stolen, from theft, or tampering. This is our fifth generation NVLink. NVLink allows us to connect multiple GPUs together, and I'll show you more of that in a second. And this is also our first generation with a reliability and availability engine. This system, this RAS system, allows us to test every single transistor, flip-flop, memory on chip, memory off chip, so that we can, in the field, determine whether a particular chip is failing. The MTBF, the mean time between failure of a supercomputer with 10,000 GPUs, is measured in hours. The mean time between failure of a supercomputer with 100,000 GPUs is measured in minutes. And so the ability for a supercomputer to run for a long period of time and train a model that could last for several months is practically impossible if we don't invent technologies to enhance its reliability. Reliability would, of course, enhance its uptime, which directly affects the cost. And then lastly, decompression engine. Data processing is one of the most important things we have to do. We added a data compression engine, decompression engine, so that we can pull data out of storage 20 times faster than what's possible today. Well, all of this represents Blackwell, and I think we have one here that's in production. During GTC, I showed you Blackwell in the prototype state. The other side? This is why we practice. 在美国就是这样子的。Ladies and gentlemen, this is Blackwell. Blackwell is in production. Incredible amounts of technology. This is our production board. This is the most complex, highest performance computer the world's ever made. This is the gray CPU. And these are, you could see each one of these Blackwell dies, 2 of them connected together. You see that? It is the largest die, the largest chip the world makes. And then we connect 2 of them together with a 10 terabyte per second link. Okay, and that makes the Blackwell computer. And the performance is incredible. Take a look at this. So, you see our the computational, the flops, the AI flops for each generation has increased by 1,000 times in 8 years. Moore's law in 8 years is something along the lines of, oh, I don't know, maybe 40, 60. And in the last 8 years, Moore's law has gone a lot less. And so just to compare, even Moore's law at its best of times compared to what Blackwell could do. So the amount of computations is incredible. And whenever we bring the computation high, the thing that happens is the cost goes down. And I'll show you. What we've done is we've increased, through its computational capability, the energy used to train a GPT-4, 2 trillion parameter, 8 trillion tokens. The amount of energy that is used has gone down by 350 times. Well, Pascal would have taken 1,000 gigawatt hours. 1,000 gigawatt hours means that it would take a gigawatt data center. The world doesn't have a gigawatt data center, but if you had a gigawatt data center, it would take a month. If you had a 100 megawatt data center, it would take about a year. And so nobody would, of course, create such a thing, and that's the reason why these large language models, ChatGPT, wasn't possible only 8 years ago. By us driving down increasing the performance, the energy efficient, while keeping and improving energy efficiency along the way, we've now taken, with Blackwell, what used to be 1,000 gigawatt hours to 3, an incredible advance. 3 gigawatt hours, if it's a 10,000 GPUs, for example, it would only take 10,000 GPUs, I guess it would take a few days, 10 days or so. So the amount of advance in just 8 years is incredible. Well, this is for inference. This is for token generation. Our token generation performance has made it possible for us to drive the energy down by 45,000 times. 17,000 joules per token, that was Pascal. 17,000 joules is kind of like 2 light bulbs running for 2 days. It would take 2 light bulbs running for 2 days amounts of energy, 200 watts running for 2 days, to generate 1 token of GPT-4. It takes about 3 tokens to generate 1 word. And so the amount of energy used necessary for Pascal to generate GPT-4 and have a ChatGPT experience with you was practically impossible. But now, we only use 0.4 joules per token, and we can generate tokens at incredible rates and very little energy. Okay, so Blackwell is just an enormous leap. Well, even so, it's not big enough. And so we have to build even larger machines. And so the way that we build it is called DGX. So this is our Blackwell chips, and it goes into DGX systems. That's why we should practice. So this is a DGX Blackwell. This is air-cooled, has 8 of these GPUs inside. Look at the size of the heat sinks on these GPUs. About 15 kilowatts, 15,000 watts, and completely air-cooled. This version supports x86, and it goes into the infrastructure that we've been shipping hoppers into. However, if you would like to have liquid cooling, we have a new system. And this new system is based on this board, and we call it MGX for modular. And this modular system, you won't be able to see this. Can they see this? Can you see this? You can? Are you? Okay. I say. And so this is the MGX system, and here's the 2 Blackwell boards. So this one node has 4 Blackwell chips. These 4 Blackwell chips, this is liquid cooled. 9 of them, well, 72 of these GPUs are then connected together with a new NVLink. This is NVLink switch 5th generation. And the NVLink switch is a technology miracle. This is the most advanced switch the world's ever made. The data rate is insane. And these switches connect every single one of these Blackwells to each other, so that we have one giant 72 GPU Blackwell. Well, the benefit of this is that in one domain, one GPU domain, this now looks like one GPU. This one GPU has 72 versus the last generation of 8, so we increased it by 9 times. The amount of bandwidth we've increased by 18 times. The AI flops we've increased by 45 times, and yet the amount of power is only 10 times. This is 100 kilowatts, and that is 10 kilowatts. And that's for one. Now, of course, well, you could always connect more of these together, and I'll show you how to do that in a second. But what's the miracle is this chip, this NVLink chip. People are starting to awaken to the importance of this NVLink chip as it connects all these different GPUs together, because the large language models are so large, it doesn't fit on just one GPU, it doesn't fit on just one node. It's going to take the entire rack of GPUs, like this new DGX that I was just standing next to hold a large language model that are tens of trillions of parameters large. NVLink switch in itself is a technology miracle. It's 50 billion transistors, 74 ports at 400 gigabits each, 4 links, cross-sectional bandwidth of 7.2 terabytes per second. But one of the important things is that it has mathematics inside the switch so that we can do reductions, which is really important in deep learning, right on the chip. And so this is what a DGX looks like now. And a lot of people ask us, they say, and there's this confusion about what NVIDIA does, and how is it possible that NVIDIA became so big building GPUs? And so there's an impression that this is what a GPU looks like. Now, this is a GPU. This is one of the most advanced GPUs in the world, but this is a gamer GPU. But you and I know that this is what a GPU looks like. This is one GPU. Ladies and gentlemen, DGX GPU.